All right, this should be a little mental exercise for us here. We should know the answer from the previous integral we did, but let's use our techniques here to help us out. I like inverse functions. So if I look at the function of y equals x squared and its inverse square root of x, we'd want to figure out what the area is within those functions. Whoops. What's going on in there? I didn't mean to click on everything. There we go. Let me color this in appropriately. Let's see here. I still keep, that scares me when I get the silhouettes like this. All right, well, we'll smile and say, hey, we're getting this region in here, even though my coloring isn't the best. All right, but that's what they said in kindergarten, right? Can't stay between the lines, and it shows in my handwriting. But we have two functions here. We have f of x equals x squared and g of x equals square root of x. I think if we think about it, that if these mirror the line y equals x, our answer should be twice the answer we got in the previous one, right? Because they're mirrors across the line of symmetry we used. But let's create a double integral out of this, where we're going to be integrating with dy, then dx, but no function in here. So this is the point 1 comma 1, this is the point 0 comma 0. So our exterior point will go from 0 to 1. And if I'm moving from y, I'm going to go from the function x squared to the function square root of x. So my first integration will be y evaluated from x squared to square root of x dx. And that's going to look like square root of x minus x squared dx. Then I'll do this integral, so that'll be x to the 1/2 minus x squared from 0 to 1, which ends up giving me, let's see, 2/3 x to the 3/2 minus x cubed over 3 evaluated from 0 to 1, or 2/3 minus 1/3, or 2/3, which is twice of 1/6. Or, yeah, twice of 1/6. And not 2/3, 1/3. 1/3, which is twice of 1/6. Sorry about that. Doubling in my head. And so this technique is really, really nice for when we know our boundaries, and actually some shapes that don't have flat boundaries on them. We can use our boundaries to find an area if we treat this area element as defining. And we'll find this gets really important also when we start looking at triple integrals and some of the boundaries that we look from there. We can also get the idea that we can get an average value. That if we have some function over a region, we can do an average value. So again, we're going to extend the idea that the average value of a function over a region is the area of the region as a divisor, and then the integral of that function over that region. This is very, very similar when we did the average value of a function in one dimension, where we did b minus a from a to b of f of x dx. That created whatever this integral was divided by that length that we were integrating across. And so we have a multi-dimensional viewpoint of that. And so what we're doing is we're taking something that will have a value that's integrated across this area, and when we divide that area back out, we get the units of the function itself. And so we can see this averaging process taking out. Let's do the example the textbook has. So we want the average value of x times cosine xy over a rectangular region of x trapped between pi and y trapped between 1. So let's do our integrations in this order. So we're going to do dy first and then dx to find our average value. So we'll do this integration first, and then we'll divide back out. Oh, and if we look at this rectangle here, right, that this is a rectangle with a length of pi and a length of 1, so its area is pi. So whatever answer we get from here, we'll divide by pi. So we'll integrate with respect to y first, so that's going to be negative sine, or a positive sign, we're going up, right? Sine of x, y, integrated, let's see, sine of xy divided by x, because of the chain rule, because it's chains, so the x's cancel out, so evaluated from 0 to 1, right? Because this would be sine of x, sine of xy with respect to y, so divided by x, because x is a constant, and the x's cancel out. So now we evaluate this from 0 to 1, so that's going to give us sine of x minus sine of 0, which is 0, so that goes away. So I think we're left with sine of x. Let's see. Sine of x, when the 1 goes in, minus sine of 0. Yep, so we're left with sine of x dx. And so we'll integrate this. That's going to be negative cosine of x evaluated from 0 to pi, which is negative 1, negative 1 minus negative positive 1. So that's going to be 1 plus 1, or 2. And so the average of this function over this entire region, or the average of the function, will be average of f of xy over region R is equal to 2 divided by pi. And so these section 2.3 kind of gives us some examples of these double integrals being more than volume.